We're on. Developing a high school okay. Uh, yeah. Society, scale Robinson, oh, stop. That's undergrad. Undergrad. Yeah. And he's going to test out Neutron Stars. Well, folks, thank you all so much for having me. Like I said, my name is Caleb Robbins, and I would probably love Neutron Star. Don't worry, if you've never even heard of a Neutron Star, which I'm sure most of you have, by the end of my presentation, you'll know just about as much as I do at the bottom. So first and foremost, just a little bit more about myself. I actually graduated in 2023 with my bachelor's in global studies from LSU. I decided to return to the university the year after to further study astrophysics and mechanical engineering. My main goal with that is to further research and further understand sustainable energy sources and their application to better transportation, propulsion, and just general life power systems. Especially my lovely parent, my fiance is also here. She is a playing genetics at LSU. She does is fantastic. Far more impressive than I can. First of all, what are put it in the business, they're one of the handful of final the dice. Um, uh, a very small cosmological, roughly about 10 kilometers. Yeah, it's a great job of demonstrating that size. I'm small. Black and that. And on 23 in density, which is 4 feet order of magnitude coordinates. Put that into a terrestrial perspective. Now Newton has a height of 8.8 kilometers, a total weight of 810 trillion pounds. Now, if we take neutron stars are equivalent in volume occupied by a sugar cube, that sugar cube would weigh on the surface of the planet Earth a trillion. Imagine 810 sugar cubes, same amount of mass as now. That's how. So, maybe questioning whether our sun very commonly known as balls, which is great for us. We can fire be here together. Our sun is a part of her thing. A couple billion years, it'll grow into a red giant, consuming Mercury, Venus, and eventually Earth. Don't worry, like I said, you've got a few million years to be sure Earth before that happens. For a few more billion years, it'll shed off this outer material, so there's nothing left of it for. But what caused the extinction? It all boils down to stars and mass. The clearest bottom track, this low mass star, that's our sun. Anything less than 8 solar masses, we'll call it lower track, become your red giant. It takes about a star with a binary partner for us. So become a same thing, a white dwarf, and after a mid period of time, all of the not of black people. However, for more massive stars, they follow the upper track. This becomes a red supergiant, floating a type 2 supernova. And depending on the mass of its core, either become a neutron star or an far right or a black hole at the top. So like I said, this all boils down to mass. But how does mass really affect? Well, look at a white dwarf. White dwarf changes this material. still 50 mass. And with more mass comes more gravity. But unlike a star, an active star, which is burning hydrogen in the core, creating heavy outward pressure, the white dwarf is essentially inert. So how does it create this pressure to counteract it? Well, the same way that you and I cannot physically occupy the exact same state of becoming a new person, electrons can do the same. They cannot physically be in the same spot. As mass increases and gravity increases, the electrons drift faster and faster, approaching the speed of light to avoid being in the same spot as one another and process of electron energy. And this pressure pushes out against gravity and counteracts it, keeping the white dwarf from collapsing. But the pressure is now done as one. When you hit a core with 1.4 solar masses, no neutron Baton limit, this electron is generated by protons and electrons slam together to form neutrons. The whole cycle begins. The neutrons have their own neutron pressure, greater power for electrons, and continue to counteract gravity. And then the neutron star, so it hits like collapse again into a black hole. So talk about this thing. So if you were to start drilling into a neutron star, first off, you're drilling with the mid-gravity. But if you start drilling into the crust of the neutron star, you know that the tiny iron far more dense than what we have. And you see, really magnitude, 10 grams per cubic centimeter. As opposed to on Earth, iron is density about 7.8 grams per cubic centimeter. Far, far more dense than what we have here on Earth. But why iron? Like I said, neutron stars are the second most dense thing in the cosmos that we know of. Certainly they'd be made of heavier materials, not just iron, which is the 26th element on the periodic table. Well, stellar astronomy 101 would teach you that stars are just living, breathing fusion reactors. They're fusing hydrogen into helium in their core in the case of our sun. And as you get to these more massive stars, they begin to form more massive, more heavier elements, such as beryllium, lithium, and the like. And they continue all the way down the periodic table until they hit number 26. Now, up until this point, these reactions are releasing energy. That's what creates the light that we see from our sun and every other star. But when you hit iron, the reactions past this require an input of energy. They're not letting anything out anymore, they're requiring put in. So that's why as soon as these stars start trying to fuse elements heavier than iron, they collapse in, the material is ejected out in a supernova, and what is left behind is a white dwarf, a neutron star, or the like. So, further in, traveling further into the crust, these iron atoms begin to give way to a neutron-rich, crystalline lattice, still solid, but a lot funkier than what we see, but it is still a BCC structure, which is still something that we see naturally occurring on Earth. As you go further into the inner crust and the upper mantle, that's when things start to get very weird, to put it scientifically. You start to see some very strange structures that are still solid material, but they're exhibiting fluid-like configuration. And in a rare case of astronomers being able to name something well, they've dubbed it nuclear pasta. Now, enough praise cannot be given to Kaplan and Horowitz for their simulations in this paper, which show these renders of this configuration. It's very, it's one thing to explain it, but it's one thing to see it. These are very dense structures that I could probably talk about for 30 minutes in themselves, but they're incredibly dense, very exotic configurations, nothing like what we see here on Earth. And honestly, the pictures kind of speak for themselves on that. But if you were to continue on past this nuclear pasta, you get to the core. And what is going on in the core? Well, as this question mark adequately puts it, we don't know. There's a wide range of theories, ranging from everything from dark matter itself to a quark gluon plasma soup. We don't know definitively. Further research is needed. But we do have a good idea of what happens up until that point. So, as for specific neutron stars, as of right now, there's roughly 4,400 confirmed. Now, this number is a very, very big lowball. We estimate that there could be upwards of billions in just our galaxy in the Large Magellanic Cloud alone. They're just very hard to detect due to their low luminosity. They're not as they die over time. But one such neutron star that you've probably heard of, even if you didn't know it was a neutron star, is the Crab Nebula, also known as Messier 1. Now this is an image from Hubble Space Telescope. It's easily one of the most popular images to come out of that program. You can see why just looking at it. There's ethereal colors, the blue especially. It's very haunting, and people love it. Now it's somewhat ironically named, but it is the first ever recorded supernova remnant in recorded history. First ever to be recorded and observed. And it was recorded by astronomers of numerous civilizations, including the Chinese, the Japanese, the Islamic, and even the Pueblo people of North America. But like I said, it's not actually a nebula, it's a type 2 supernova remnant. And in its core, somewhere right around here, it hosts a rapidly spinning neutron star. This is a better view of it from JWST, in which you can really see that ethereal blue color. Now it's not just pretty for pretty's sake. This blue color is generated by electrons that are zipping around near the speed of light throughout this neutron star's magnetic field as it rapidly moves. We're going to talk a little bit more about the Crab Nebula in a little bit. Another example is SN 1987A. Like I said, astronomers' names, not the best. This supernova remnant, recorded in, wouldn't you guess it, 1987, was the closest supernova to be seen since Kepler's supernova in 1604 CE. It's a bit of a big deal. In this image, it's not this is the Tarantula Nebula. It's actually this little Christmas tree copper star looking right there. Now, SN 1987, like I said, seen as a supernova remnant, but recently made headlines this year in spring when it was confirmed to be a neutron star, which caused it, thanks to JWST. You can see in these images here, what finally confirmed it is this presence of 5 times ionized argon. And if you're familiar with argon, it is a noble gas. Noble gases are the most stable element on the periodic table. They're inert, they've got a perfect amount of electrons, they're perfectly happy as they are. So to convince it to give or take 1 extra electron is no small feat, much less 5. That really speaks to the power of these neutron stars. Now, not all neutron stars are cookie cutter the same. There's 2 major subclasses that we know about at present of neutron stars. The first and most popular being pulsar. This is an artist representation of a pulsar. Pulsars are neutron stars which are spinning very rapidly, and they're also spewing radiation in the form of gamma rays out along its magnetic axis. So you see this here, like I said, artist representation. But what does it look like true? Well, thanks to the Chandra X-ray Observatory, we have images of a real pulsar. This is in the Vela constellation, and you can see very faintly its relativistic jet of those gamma rays that it is emitting. Now, in that picture, it doesn't look very long, but that jet is about 0.7 light years in distance. That's enough to travel the distance between the Earth and the Sun 44,000 times. It's very, very long. Speaking of examples of pulsars, the Crab Nebula is one. Not only is it rapidly spinning, it is also spewing out radiation, which you can kind of see in this image. If you focus your attention right here, you can see it kind of looks like when you drop a pebble in a pond. Those emanating waves show the wave pattern of those electrons and that radiation that's being spewed out. Still image captures are pretty good, but even better is this time lapse of 10 Hubble exposures from the Crab Nebula, which you can really see that wave motion of it flowing out. So hidden in this popular image not only is a neutron star, but it's a pulsar. Now the other special type of neutron star, significantly far less known. Pulsar, the number of recorded pulsars ranges in roughly the thousands. Magnetars, we have a confirmed 24 out of a candidate list of 26. They're far more rare. They're far more difficult to detect. Now, magnetic fields, if you're not familiar with magnetic fields of celestial bodies, you should be. Earth is one of the main reasons that you're still alive. You, me, all of us. It protects us from harmful radiation from the sun. And an average neutron star has a magnetic field that's 10 to the 12 times stronger than Earth. So already far blowing us out of the water. A magnetar is 1,000 times stronger than even that. So why is this the case? Well, we're not quite sure again. Further study. But the reigning theory right now is that it's a result of a magnetohydrodynamic dynamo process. I know that's a very big word. Basically, it just means that it's a mechanical, it's something that's converting mechanical energy into electrical energy, which is further strengthening that magnetic field. And as a result of this process, it's creating a very delicate system in this neutron star, in which the slightest disruption to the magnetic field or the solid crust will release an explosive expulsion of energy that we've dubbed starquakes. Now this is an artist representation, but these are not purely theoretical. We have recorded these. In fact, in December of 2005, the magnetar SGR 180620 released one said starquakes. This is a render of it. It traveled 50,000 light years to Earth, where it temporarily disrupted our ionosphere and overloaded the Swift Observatory, whose whole purpose was to observe gamma rays like this. This event was so powerful that in this fraction of a second, it released more energy that the sun will generate in 150,000 years. So there's no joke. Yeah. So this is all well and good, but like I said, and like I've said multiple times, there are numerous gaps in our understanding. We don't know what's going on in the core. We don't know how to detect them better. But further study is working towards this. And one particular theory that I'm interested in, that I want you to take with a grain of salt, because it is still highly theoretical. Papers talking about this, they're either very old or yet to be published, but I do think it's an interesting theory that we shouldn't discard just yet. Regards this Chandrasekhar limit. So like I said, from 1.4 to 2.2 solar masses, a neutron star can exist. Anything below that, it's a white dwarf. Anything above that, it's a black hole. But is this completely black and white? Or is there some variation in there? Is a neutron star at 2.2 solar masses exactly the same as a neutron star at 1.4 solar masses? We don't know. But one theory says that as you get closer to that 2.2 solar mass limit, some quantum weirdness might start happening. So protons, neutrons, they're made out of these things called quarks, an elementary particle. And as you get closer to that limit, before you actually become a black hole, but as that pressure becomes so insurmountable, it's possible that these protons and neutrons, these basics of an atom, might break down into their constituent quarks, releasing them into a sort of quark soup, to put it scientifically. And these are just free floating. Now, like I said, grain of salt. We don't know. We haven't seen any of these, but it is still a theoretical thing that people are doing research in that I personally find very interesting. But what is the point? Why are we studying neutron stars? After all, our star won't be one, so shouldn't we be focusing on white dwarfs, red giants, and the like? And the point of it all wraps back into a little something called the Big Bang. Now, whoever made this image, I hope they're getting their residuals, because I've seen it used more than any other picture in astronomy.
Oh, yeah.
But I want you to ignore all of it except for this bright flash right here. That is the time that happened in the, not even a full second, 10 to the negative 30 milliseconds after the Big Bang, in which all those elementary particles, quarks, gluons, all of that, were just free floating in a soup, the entire universe around. And then as time went on, they were forced into protons and neutrons, and they were forced into atoms and molecules, and they were forced into planets and stars, and eventually they were forced into you and me. But that kind of sounds familiar. That kind of sounds like what we think might be going on in a neutron star. And if that is the case, then a neutron star, its core, is essentially a living time capsule of the Big Bang, of the very, very first milliseconds of our universe's life. So I think that warrants further study, because even if it doesn't pan out as we expect it to, even if all of our theories are moot and it's all out the window, it's still going to help us better understand quantum phenomena and the universe around us at large. That's all I've got. I'll open up to any questions.
The release of energy from the star flare, how does that compare to the gamma ray?
I don't know the exact figure comparison.
I saw somewhere it said there was a GRB about 10,000 years ago was detected in that.
In my understanding of that wave, I don't know the exact time it took to travel that great distance. But I'd imagine it's probably far greater than your average gamma ray.
That bottom image, that's a combined X-ray and video, isn't it? That bottom left image?
Yes, so that's the opposite image.
Yeah, that's a really good one, because you can see the jet on it.
Mhm.
Are there any planets in that nebula, like that can, where life can like function like Earth?
Well, the habitability question is always a bit of a loaded one. I don't know off the top of my head, and that's one of those things where it's the limits of our detection versus what we expect. So they're very likely, there very likely are planets in that supernova limit or around it, but whether or not they're sustainable for life is another story. And especially around the neutron star, if they weren't completely decimated by the supernova, the chances of them being habitable are very low, because unlike our star, which is giving us radiation through fusion, the only thing that's left in white dwarf neutron stars are just the heat and the temperature from when it was fusing that's slowly petering out over time. That's why they'll become a neutron star far longer lifespan than a white dwarf. But a white dwarf will eventually become a black dwarf because it will have no luminosity left to give. Yes.
Most illustrations of pulsars show the star with the two spikes coming out of the axes, but you also showed some pictures that showed it as a ripple effect, like dropping a pebble in the pond. So, which way does it really behave, or can it go either way?
It all depends on our viewing angle. So for this pond, it's more likely that it is, if I'm us, it's like this, and it's rotating, creating a bit of a circle. So it's emanating outward. So we don't really see I guess, from our perspective, the southernmost jet, but that top one is what we're seeing creating the wave. As opposed to if we were seeing one edge on, where we could see both jets, that would be what changes the image. So it's all observation. Yes.
Kind of sort of a math question. So, the gas laws that govern a lot of normal stellar processes,
Mhm.
these laws that you were talking about, the mathematics of the partial pressure inside the neutron star, is basically the same thing as the mathematical as the gas law?
I think it's more akin to like quantum exclusion principles, where you like can't have two electrons occupying the same state. You can't have them with the same quantum numbers. In my understanding, it's more akin to that.
So it's not like a partial pressure situation.
If so, that was a little outside of the scope of my research for this talk. It very well might be, and then a little bit beyond my understanding.
Well, beyond that.
But from my understanding, it's more akin to the Pauli exclusion principle, which is what states that electrons can't be in the same state and in the same space.
So then our understanding of the mechanics within the neutron star as far as its expansion is more on the quantum mechanics side of science and not so much on the classical side.
Because once, like I was saying in the anatomy section, once you get into that, a lot of our classical like materials and the like are kind of out of the window, and we're getting these exotic materials, some of which do follow, standard laws, like especially that which is still body-centric cubic solid structure. But if you get into like the upper mantle, the inner crust and the upper mantle, things start getting very weird.
What I've never understood is how the quantum mechanics and the classical overlap. I mean, clearly the thing is not collapsed. There it is.
Right.
But then how?
From all of my study, it all depends on how fast it's going. So the closer you get to the speed of light, the more you're undergoing relativistic and quantum phenomena.
How do people plan to study going forward?
Right now, it's a lot of theory. There's not a lot of observation that can really go on. It's a lot of, like what I showed in the class, a lot of simulation. Based on what we understand and what we can observe, running that through simulations and tests and seeing if it matches what theory says. Because unfortunately, we can't drill into it, see what the material down there looks like. It would sure would make things a whole lot easier.
How does this line of inquiry inform your research interest and/or career trajectory in transportation systems and modes?
Not in the slightest. Not in the slightest. This was actually a talk I gave in a astrophysics class, and my friends that run astronomy on tap over at the Varsity Theater needed a speaker, and they asked if I would do it, so I said yeah. Neutron stars and compact objects I do find tremendously interesting, but unfortunately, likely not a lot in the realm of sustainable transportation.
It's just all, it is awesome.
It's awesome. We're talking. Any other questions?
Yeah, on that first slide, the outer crust is actually iron,
Yes, sir.
and that's left over from the original supernova.
Absolutely.
Because iron's the last thing.
Absolutely. That's the last thing we form. So when it collapses, that outer layer is pure iron.
But not iron like on Earth.
Yeah, it's far more dense. Like 10 to the 7 times more dense than that on Earth. And that's just due to that extreme pressure of the rest of the
Now, in
sun.
the moment of the supernova, though, it forms all manner of other elements.
That
All
the
of
ejecta
And so
forms.
they're all ejected, and basically just iron.
Yeah,
particles.
absolutely. That's how heavier elements than iron are all formed in supernova.
Yeah, do you think we'll ever get to the point that we can harness energy very consistently?
I hope so. There's so many different methods that we're pursuing that I'm hoping to research on. I don't have the chance to do it just yet, but that is my goal. And it's just, we'll just have to wait and see.
We can
0.08 solar masses. The mass of these objects is not sufficient to begin hydrogen fusion. So it has luminosity due to its temperature, but it is not doing fusion, so it is not it's not an actual star. It's a brown dwarf. Brown dwarfs is kind of a tangent. Brown dwarfs are a bit of a pain in the butt because when we're trying to detect exoplanets, especially through transit, which is when a body passes in front of the sun and reduces its luminosity. Brown dwarfs are one of the potential false positives that we can get instead of an actual exoplanet. So they're a bit of a pain because obviously they're not going to be habitable. Please get out of the way so you can see exoplanets.
How can you tell them apart from like a gas planet?
So much
Like when you're,
smaller.
like when you're searching for exoplanets.
So the gas that's made that constitutes a brown dwarf is very different than the volatile materials that make up a gas giant like Jupiter or Saturn. Because this is not; those are very icy, very cold, as opposed to a brown dwarf, which is still the same gas that a star would form out of, just not enough of it to begin fusion.
So do you ever got positive or ground actually on the way?
We have, and yeah, false positives happen all the time in the exoplanet detection community. There are folks who are affectionately dubbed planet killers because they seek out confirmed exoplanets and try and see whether or not they are actually exoplanets.
But since they radiate mostly in infrared, you have any way to come up with it?
If they're near enough, I don't know this for a fact, but I would assume as they are very small and not emitting a ton of light, they're very hard to detect, especially in the presence of brighter objects around. So theoretically, Webb should be able to, but whether or not it actually can. I don't know off the top of my head of any that have been detected by Webb, brown dwarf specifically. that have been detected and or confirmed.
Well, wouldn't you need to be able to live enough of the, spectrum for spectral analysis?
Yes, and then spectroscopy, as well as actually looking at the transit lines as opposed to like what you would see with an exoplanet. What you see with an exoplanet and what you see with brown dwarf, they are slightly different. They get some luminosity and the like. So using those methods, you can rule it out. But you know, if it's a smaller brown dwarf, I think it's harder to behave more like a small planet might. But yes, that is very true. Looking at absorption and emission spectrum, it should help rule out false positives.
The light, tells you how big it is, so how do you go how big the star is?
So, yes, when an object transits another sun, the dip in luminosity can tell you the radius of that object, which is all very mad. But it can, if you have sufficient observations, it can tell you the radius of that.
Are stars being born, or they're all born simply of Big Bang?
They are being born. So when you're looking at I don't have any that I think good represented here, but if you're looking in nebula and clouds, if you're seeing a lot of blue light, that's young stars. Now that's not the same as in the Crab Nebula, of course, but if you're seeing blue stars, those are young stars. The redder it is, the older it is. So stars are being formed constantly in nebula and just star. I mean, the Pillars of Creation is a super popular image from Hubble and James Webb, and that is, you can see so many blue stars there because it is just a massive gas and dust. They're just collapsing in to form these stars.
The most famous would probably be the 4 in, 42, Orion. Yeah, the Orion. And they've seen over a long period photographs, stars actually light up in the Orion, and you've actually seen them come out.
It is.
Yeah, they released, I think a 400 megabyte photograph of Orion online, and then I couldn't download that one, but I downloaded the 42 megabyte. That's one for just cloud creation. You can see stars, bow shots, where the nebula streams past, it makes like a bow wave. It's pretty cool.
But that thing that came through and knocked everything, how long that was that?
So we encountered it in 2005. I don't know off the top of my head when the star quake happened, and I don't know if that's something that we know. I assume if we knew the energy, we would know how fast it was traveling, but it got to us in 2005, in December of 2005, and it traveled 50,000 light years. I don't know exactly how long it took to travel that time off the top of my head, but regardless, to travel that far and to maintain that much energy is something.
They will be lucky enough to do drop off.
And everyone's waiting.
That'd be
Everyone's
awesome.
waiting.
We had it all 540 years ago.
Yeah, I know. It'll take a little minute, but we'll have to see.
It would be amazing.
It will make a lot of people very happy.
I got one more about brown dwarfs, because it's rare to find somebody who knows anything about brown dwarfs. So there's I've heard theories about planet X on our solar system and search for planet X. And I've heard some theories that say that we could be a binary system with a brown dwarf as planet X. Have you heard any updates on that?
I know Planet X was kind of making a splash.
A long time ago.
Yeah, and I know I talked about it with some folks earlier this year. If it's possible that there is a object with just a massive orbital axis and period that might swing through, but from what I gathered when we were looking into it, most simulations say that it's probably not. As for us being a binary system with a brown dwarf, the brown dwarf would have to be far closer for it to be gravitationally bound to the sun.
So no binary brown dwarf.
Not Planet X, maybe, not likely, but maybe brown dwarf, very, very likely. Just due to its mass, and then even Planet X, if it does exist, it's probably very small. Probably more akin to like comet that you get through once every 300 years.
Well, 1.4 million years, July 710 is going to pass 2/10 of the light year from the sun, so that's interesting. And we got 0.6 in that for the sun, so that'll shake things up pretty good.
Yeah.
What year is it?
Yeah, 1.4 million years from now. I'll put it on my calendar.
Yeah. I'll put it, right next to us and Andromeda.
By the round, they're gonna see a heck of a meteor shower.
Any more questions?
That was awesome. Appreciate it.
Thank you, that was
Thank you all so much for having me. Thanks, Ben, for inviting me. I would stick around, but unfortunately, I have quantum homework to do. That's due tonight. So I'm gonna check, but thanks again, y'all.
Make sure to come visit us. This was his first time ever out at the observatory.
It's pretty shameful too, because I am from Gonzales. So
Okay, I live in Gonzales.
unfortunately, I work in a restaurant, so that makes Fridays and Saturdays.
Yeah.
Well, thank you so much. Feel bad.
Thank you all so much.
Well, it's been kind of an exciting month.